Hi, my name is Megan Kizmatka. I work for John Deere, and I will be presenting with Arvind Husagrahara from MathWorks today. We'll be talking about enabling physics and empirical-based algorithms with Spark using MATLAB in Databricks. So I'm a senior engineer at John Deere Power Systems within R&D. I have background in diesel engine calibration, tuning, and performance. I also have background in embedded controls, test and methodology development, and I currently work in engine damage modeling based on mechanical fatigue and wear development and implementation.
Hi, and my name is Arvind Husagrahara. I'm the Chief Solution Architect at the MathWorks and the technical lead of a small team of engineers that focuses on getting our technology working with Spark and working with the rest of the software stack with experience in helping clients like Megan be able to solve their technical problems.
So we'll be talking about, can't see the slides. We'll first be talking about an introduction to John Deere and MathWorks, and then we'll talk about the objective and problem statements of our project. We'll give an introduction to predictive damage modeling. We'll talk about the requirements and the challenges within this project. And we'll also go into solutions and a demo as pertaining to our project. And we'll go over some conclusions we have. So John Deere is a company that's been around since 1837, and we're a world leader in providing advanced products and services for those who are committed and linked to the land. Those who cultivate, harvest, transform, enrich, and build upon the land to create to meet the needs of the world, the dramatically increasing need for food, fuel, shelter, and infrastructure. We're a leading solutions provider of heavy-duty off-road equipment within agricultural construction and forest and machinery. And John Deere Power Systems and Manufacturing manufactures its own heavy-duty diesel engines and drivetrains for internal and external applications. A component of our fundamental design is our strong desire and desire for reliability and durability, as well as our utmost performance of our customer, which is rooted in our deep understanding of our customer usage cycles. Using physics and mechanical fatigue-based damage models, we can understand the durability of our manufactured product.
The MathWorks is the maker of MATLAB and Simulink, our flagship products for expressing technical computing workflows, MATLAB being a textual environment and Simulink being a graphical environment for people to build their models, to perform their data analysis, and to be able to express their analytics in our products and allow them to stay at a level of abstraction with domain-specific toolboxes.
John Deere is a multifaceted company with diesel engines specifically engineered into our equipment from all sizes to all varieties. We're most well known for our large row crop tractors and harvesting equipment, but John Deere makes equipment all the way down from lawn and garden equipment to compact and utility tractors. We also are a big player in construction and forestry, and John Deere Power Systems, as a diesel engine company, has a big presence within OEM engine manufacturing. And we develop engines such that they go in large yachts, military defense equipment, and commercial and industrial generators. So now I'll talk about our application and our project. So I'll talk about our problem statement first. At a business level, John Deere is seeking to understand the product usage and design the best-in-class uptime and durability and performance. We're also seeking to improve damage model calculations by increasing agility of the development, migrating onboard predictive maintenance models to the cloud. At a technical level, we want to reduce the time to execution of these damage models, alleviate the demand on the scarce compute resources within the vehicle, enable deep discovery of the data, apply insight into the design and development process, and maximize efficiency by leveraging cloud compute on telematic fleet data. So I want to talk a little bit about the two concepts of onboard versus offboard damage modeling, and then I'll get into damage modeling. Onboard is a concept of basically taking physical conditions and calculating a control or action using an embedded controller and performing and putting that into the embedded controls to calculate and give out the best performance and emissions. At that embedded controller, what you can also do is calculate damage models to do two things. One, diagnostic cross-checks, and two, predictive maintenance or prognostics. We would calculate damage accumulation and damage increment of a specific component on the engine. We'd then send that data back up to the cloud and the vehicle to alert the vehicle or the customer to alert them that they may want to come in for maintenance. There are a couple issues with this model, though. One is the rigorous embedded software development process that drives a longer time to insight. The good things about the software V&V process slows down how we develop our components within the vehicle. The second is that we are limited to physical resources within the embedded controller, which limits the number of damage models we can put on the controller at once. And the third is the loss of the physical transient data like engine speed and temperatures and pressures that can tell us so much about that customer usage cycles so that we can develop good product that we know will suit the customer's needs. The next is offboard damage modeling. This is a simple concept of taking a telematic data logger and collecting data passively and putting that into a cloud plus compute environment. At that cloud compute environment, we would then execute our damage models there, which helps us exponentially speed up the time to insight, alleviate stress on the controller, and have more damage models and gain deeper insight from transient log data so that we can rebuild those cycles within our dyno labs. So let's talk about engine damage modeling, the root of predictive maintenance. So damage is generally defined as 1 over n, where n is the number of cycles or hours to failure, as pertaining to the SN curve. An SN curve is a stressor versus number of cycle curves. And damage modeling is an incremental analysis of stress at each event or cycle, which then can be summed using Miner's rule. On the right-hand side, you'll see a failed bellows, which is in alignment with the fatigue-based damage model strategy. So to do fatigue calculations, you must understand the two concepts of fatigue cycling and rain flow counting. Many fatigue-based damage models are not based on time or events at a given level. Rather, they're based on sequence in which the events occurred. Materials have memory.
The best way that I know how to describe this phenomenon is with the two paperclip examples, one at time at level and the other at cyclical load. On the left side, you'll see that I pick up a paperclip and I unwind it a total of 1080 degrees, putting a very high maximum amount of stress on this paperclip. However, I'll set it down and it should never fail. On the right side, you'll see that I pick up another paperclip and I never unwind it nearly as high as 1080 degrees, never putting that high maximum amount of stress on the paperclip. what you'll notice is that I cycle the paperclip, causing a fatigue effect. This is alternating stress, and this eventually will fracture the paperclip. As you can see, it's starting to bend and fracture, and eventually I will be able to fail it and pull it apart, which will equal a damage equal to 1, failure.
So let's talk about a real-world predictive maintenance model feature. So a really cool one that I like to talk about, and a very simple one at the same time, is turbo wheel failure, or turbo LCF. For those that don't know, a turbo basically supplies compressed air to an engine combustion cylinder, which increases efficiency of the engine and also increases the power. So if we have a failed compressor turbo wheel, we'll have loss of compression and we'll also have loss of power. So let's take a farmer out in the field who only has a very finite window in fall to harvest his crops. For those that don't know, many farmers nowadays actually harvest 24/7, and they can't actually tolerate any downtime when they're harvesting, because if they're not able to get all that time, they may not be able to get all their crop out of the field, and they risk losing money from lost crop. So if we can alert the customer of that happening before they can get to the dealer and maintain their vehicle before that ever happens. So how do we do predictive maintenance? There are 5 main steps. The first is using a physics-based first principle equation. As you'll see on the right, we have turbo wheel stress. The values that go into this are a coefficient, a geometric wheel diameter, and the transient input of turbo speed. We then would calculate virtual stress or strain with those log telematic data input using the input of turbo speed and calculate the output of turbo stress over a drive cycle. We then would rain flow count each of these stress strain cycles or sequences such that we could solve for the damage increment in the drive cycle. After this, we would then calculate the damage accumulation. And as you'll see on the right, what you'll see is over one drive cycle that's about 45 minutes long, we have about a little less than 400 sequences or cycles occurring. What you'll see is the damage ratcheting up and the remaining useful life ratcheting down. Eventually, over time, the damage will equal 1, which will result in a failed turbo wheel, or remaining useful life of 0, meaning no more useful life of that turbo wheel. Now I'll talk about the challenges and requirements of this project. The complex physical phenomenon of these models are very hard to model using purely reactive-based statistics. We'd like to apply the proven statistical techniques to the data, and we'd also like to keep the domain expert focused on their line of expertise. A lot of engineers and scientists already use MATLAB and Simulink for their great toolboxes. We don't want to have them recode everything and learn a different language, so we want to keep them within their domain of MATLAB and Simulink. The third is currently engineers and scientists have little to no control over the upstream data engineering transforms. And we want to enable self-service solutions for the ETL needs in the existing infrastructure. The fourth is that we'd like to isolate the data in the most damaging portions of the cycle, such that we can explore and reintegrate those conditions back into our testing and field tests, such that we can create the most durable product. So we want to enable interactive exploration of the data back in MATLAB. And the fifth is handling the time-dependent or state-based calculations within Spark, we want to enable the pushdown of the MATLAB analytics like rainflow counting at a gross parallelization level like the vehicle on the cluster. So let's talk about the big picture. First, I'll talk about the data, then I'll talk about the architecture of the data pipeline, and then I'll get into the specific ETL process. So currently, we have terabytes of data growing exponentially year over year, and we're using an EDL, or an enterprise data lake, and specifically we use AWS S3 buckets. Our data arrives encrypted and in proprietary file formats, and we have a diverse data file set. We have structured data, hierarchical metadata, and unstructured log data. So I'll talk about the architecture of our data pipeline. First, I want to talk about the first step in creating the damage model analytics, using those great MATLAB and Simulink toolboxes that were robustly engineered for engineers and scientists. Once we do this, we can compile the code, the data algorithms, as well as ETL processes that make the data analysis ready using a MATLAB SDK compiler. We would then create Java or .jar files such that they could be used on a Databricks MATLAB provision cluster. The next step is to actually flow the data in and to compute on it. First, we take the data from a telematic data logger and send it to a cell network where it then lands on an on-prem file server. From that on-prem file server, we use Apache NiFi as our ETL process. At Apache NiFi, we employ a MATLAB production server client call, which holds our ETL algorithm that we developed within MATLAB, decoding, cleaning, and enriching our data. After we do this, we ingest the data into the EDL such that it can be mounted on a Databricks file server. From this Databricks file server, we can now run our MATLAB analytics for damage modeling and predictive maintenance on a Databricks cluster that is provisioned to run MATLAB code. Now we can calculate vehicle damage at scale for our test fleet vehicles or customer vehicle population. Now I want to specifically talk about our ETL process, or our extract, transform, load process of the data. The data can be taken either from EDL or AWS S3 raw bucket or the on-prem server. And then within NiFi, the MATLAB production server client call would run a proprietary decoder to decrypt the contents into a serial environment, then process and enrich the log metadata and the raw text contents of the input files, the transactional transient data, and then we would cleanse the data and perform data anomaly detection. After that, we would create the tabular structured analysis-ready data that can be used within Databricks or a data lake, and we would output it to a parquet to our EDL such that it could be mounted onto the DBFS or the Databricks file server for usage within the cloud compute environment. Now I'll turn it over to Arvind for a quick demonstration.
This is a quick demonstration of the workflows to leverage Databricks from MATLAB. Creating a shared Spark session in MATLAB would allow users to specify Spark properties and build a shared Spark context that leverages Databricks Connect to connect to a Databricks cluster running on the cloud. And this handle the Spark session can be used to point to data, to load data from the cloud-based storage and slice it and dice it from within the MATLAB environment. Once the data is loaded, MATLAB offers a lot of features to allow users to explore their data, if necessary, inspecting it through the rich visualization available in MATLAB, and focusing on areas of interest in their stored data, as well as a lot of functions that are designed to simplify cleansing and fixing the data integrity issues that is required to make the data ready for analysis. In this particular case, our turbocharger had missing values that we use the fill missing function to fill in, allowing us to perform cycle counting. To develop a predictive model, we leverage domain-specific toolboxes, in this case the predictive maintenance toolbox, and the rainflow function to be able to quickly visualize the range and averages of our cycles in our given data set. This allows us to very quickly apply models to the data. In this case, a simplified model that uses the rainflow function in the predictive maintenance toolbox allows us to measure increments of damage as it builds up through the drive cycle. The models developed in MATLAB can be pushed down to Databricks Spark using the MATLAB compiler SDK. The resulting jar file from this exercise can be used on Databricks either as a library or as a Spark submit job. In this particular example, we compile it into a Spark submit job and show how you could use the data engineering features to quickly stage the job for execution on Databricks Spark. This particular jar file is pushed up to the cluster, at which point the user can declaratively define his cluster infrastructure, specifying the scale of how many Spark workers he needs. Enabling the MATLAB runtime will make this a MATLAB capable cluster. Once you have a MATLAB capable cluster, that cluster definition, which contains the necessary configuration to execute the job, can be attached to a job object, giving it a name. By adjusting the properties of the job, one can attach the cluster definition to the job, as well as other features of the jobs, such as enabling job status notifications on start, success, and failure, and specifying what to run as a part of the job, in this case pointing it to a jar file. The ability to set the task allows us to trigger this as a part of our execution. And finally, it's possible to control the job itself by creating the job on the Databricks system, executing it, and refreshing details about the job. On completion, the results can be fetched from the output location and visualized in MATLAB.
And now let's take a quick look at the tooling and the workflows for expressing what Megan was discussing. For starters, it's possible to elastically provision MATLAB-based compute on Spark that has access to the underlying cloud data storage layers and allows users such as Megan to perform data engineering automation by creating jobs and scheduling them or kicking them off on demand, working with the security layers that Databricks offers. The first step of her journey starts with the interactive exploration of her data, where she can get a selection of her data for analysis, slice it, dice it, bring it into MATLAB for efficient exploration of the data that is sitting on the cloud. This gives her access to forensic portions of her data, isolating sections of interest, and enables the large array of MATLAB domain-specific toolboxes and apps to write less and do more. The last part of the workflow would be to take this
compute that is being designed and push it down to run on the cluster. And this can be done either as Spark Submit jobs or as libraries that run on existing clusters, enabling MATLAB users multiple semantics to be able to execute their analytics at scale on a Spark cluster.
And so we have a couple conclusions that we've come to within this project. Is that we have come to better insight with the product usage in a fraction of the time by leveraging the best-in-class tooling, Databricks and MathWork products. Domain specialized engineers can now use their existing code and models within a Spark environment with little to no rework. And engineers and scientists can self-serve their upstream ETL infrastructure needs to suit their analytics requirements. And we get the same great insight at scale. So thanks very much for joining our presentation, and we'll now open it up to questions.